Welcome back. We are now going to do some investigation into how we get the equation that we use to work out the force between two objects, all right? So, what we're going to do now is we're going to look at what happens when the mass of the two objects involved change. We're only going to look at two objects for now because we want to simplify it. Remember that you are attracted to everything around you, and everything around you is attracted to you. So actually you do like your science book, okay? But let's just keep it as two objects just to simplify it. Here we go. So here we've got two masses, which are quite big, which are being pulled by giants. Let's just go with that. What I need you to take note of, number one, is in the situation I have on the board at the moment, both masses are experiencing the same force, 33,4 newtons. Why are they experiencing the same force? Newton's third law. Okay, every object, when a body A exerts a force on body B exerts the same force on body A, but in the opposite direction. So the size of the force they experience is the same. What I want you to take note of is the black arrows at the top, because you can see that the pink mass, which is mass 2, is attracted to the blue one, and the blue one is attracted to the pink one. Here we're using billions of kilograms just because we want a decent size force. Let's see what happens if I take mass 1 and I double its mass. So now I make it 4. If we look at the force, number 1, we notice that it got bigger, but number 2, we notice that it doubled. So it got bigger because the masses are bigger, but it doubled. It got twice as big because the mass was twice as big. So we're going to double the mass of mass 1, and now it becomes 66,7 newtons. So we doubled the force. Let's double mass 2. That means we need to go to 8. Now I've got 133,5. So I had 66,7. I now have 133,5. I doubled the force again. Compared to the first one, the first time we did this, we had 33,4. I've doubled one mass. Then I doubled the second mass, so I made it 4 times bigger in terms of all the masses if I multiply them together. And the force became 4 times bigger. That tells me there's a relationship, a mathematical relationship between the force and the masses. We just made the masses bigger. Let's make the masses smaller. So I'm going to reset. We're back to what we started with the 33,4. Let's make mass 2 smaller. Just by 1. Now it's 25 because we've made the mass smaller. Let's make them both 2. It's now 16,7. So I halved the mass, and now the force is half. So the smaller the masses, the smaller the force between them. Mass is important, but it's about both masses. It's not just about the one. That's really important because it tells us we're interacting two bodies. Both bodies are important. You can't forget about one. You've got to have them both. Let's put this into some sort of way of looking at it. What we realized is that if I increase mass, I increase force. What we actually say is that force is directly proportional to the first mass times the second mass. I know that feels weird, but both work together. And how do I know it's times? Because I showed you that if I double both masses, force doubles twice. Okay, why? Because I would be going 2 times mass 1 and 2 times mass 2. 2 times 2 is 4. If it becomes 4 times bigger, then force becomes 4 times bigger. Be careful when we describe this. I can't say that it's directly proportional just to mass. Remember, I said to you, it depends on both masses, and they have to be multiplied together. Be careful as well that you don't add the masses. It's got to be multiplied together. There may be situations where your masses are the same. That's fine. Doesn't matter. It doesn't matter about the value. It's about the fact that they have to be multiplied together. So, force between the two objects is directly proportional to the product of the two masses, M1 and M2. Got that one. What happens when we change the distance? Now here the maths gets a little hairy. So we're back here. Let's reset this back to the original, 33,4. I'm going to change the distance. So I'm going to, let's say, I'm going to make them closer together, and let's half the distance. So we're going to go to 2.6, 2.2. It's getting very close because they're very big. There we go. Oh, now look what happened. I halved the distance. So if we're thinking of what we did with mass, when I halved the mass, I halved the force. I've got closer together, but the forces got bigger. Okay, so if the force got bigger, but why didn't it just double? We've done inverse proportion somewhere else before, so why didn't it just double? And this was quite important. Remember when Newton would have done this, he would have done all the calculations by hand, didn't have calculators, which is scary, all by hand. So this would have taken lots and lots of data and drawing graphs and all sorts of things. But if we think about it again, we've seen that value before, the 133,5. We started with 33,4. Remember when I doubled the mass twice, we made the force 4 times bigger, which is 133,5. Well, I halved the distance, and it became 4 times bigger. Maybe there's a square involved. Let's think about it. Let's reset. Now I'm going to see if I can make the distance twice as big. So I'm going to move him away to that side. There we go. Let's just make him 6. There we go. Let's go him to the other side so I don't get him off the... Ooh. That's 8. I've now doubled the distance. Look how small that force is now. That's significantly smaller. So I went from 33,4 to 8,3. That's a big difference. So by doubling the distance, we know there's an inverse relationship, but I didn't half the force. In fact, it's 4 times smaller. And if some of you have got your calculators out, you're going to go, but it's not exactly 4 times smaller. It's because we're going to 1 decimal place. If we kept all the decimals in, we would see it. But 1 decimal place is enough. I doubled force, doubled distance, and force became 4 times smaller. I'm seeing a relationship because 2 squared is 4. Okay, the square is becoming important. If we look again, just quickly, so let me double this mass 1's mass. We double what that force was. As soon as I make the distance smaller, the force gets bigger much quicker. So distance actually has a bigger role to play than mass, because a small change in distance makes a big change in the force. That's very important. If we now look at the relationship, so we realize that force increased when distance decreased, and we realized that force decreased when distance increased, but that's not enough. We want the inverse proportionality, so that tells me that force is inversely proportional to 1 over r squared. That r squared is so important, all right, when we do this. You can't leave that r squared out. How do we put this all together? Well, I've now said to you that we have this relationship between all my factors. Okay? I can write it as m1, m2 over r squared. That's directly proportional to m1, m2, inversely proportional to r squared. We can't use the proportionality, so we have to introduce a constant to get rid of that. That constant is g m1 m2 over r squared. There's our equation. We're going to take a small ad break, and we'll see you in a couple of minutes.